Now let's look at the problem on second law of thermodynamics. But before going into problems, I want to highlight a small mistake that I've done in the previous lecture. Here I have written and said that COP is equal to desired effect by Qn. It is not Qn, it is actually desired effect by work done. Right, these formulas are correct, but here I have given it as wrong. So with this correction, let's proceed to the problem. So as I told in previous lectures, the questions for the problems that I'll be solving will be provided in the link that is given in the description. So please go there, download the document, and then follow the lecture along with those questions. And these questions are taken from the material of ACE, so credit has to be given to them. So let's start with the first question. Let's start with simpler questions. In the first question, it is given that a heat engine working on Carnot cycle receives heat at a rate of 40 kilowatt from a source of 1200 Kelvin and rejects it to a sink at 300 Kelvin. The heat rejected is. So this is 1200 Kelvin and this is 300 Kelvin. Here this receives heat at a rate of 40. Qn is equal to 40 kilowatt, and it is given as heat engine and it is Carnot. So we know that for Carnot, 1 minus efficiency is equal to 1 minus QR by Qin is equal to 1 minus TL by PH. So this implies QR by Qin is equal to TL by PH. So QR is what you want to find, by Qn is 40 is equal to TL is 300 by PH. So that gives QR is equal to 10 kilowatts. So this is a very simple problem. So look at it as if Carnot cycle is given, or reversible cycle also in some cases, you can directly use the temperature limits to find the efficiencies. So let's go to the second question. Okay, in the second question, a Carnot refrigerator is working between reservoirs of minus 30 degrees centigrade and 44 degrees centigrade. What is the coefficient of performance? If the actual refrigerator has a coefficient of performance that is 70% of the Carnot value, estimate the refrigerating effect per kilowatt of power consumption. So it is given that Carnot and it is a refrigerator. Reservoirs of refrigerator works like this, and here it is minus 30 plus 273 Kelvin. Remember, all temperatures have to be in Kelvin. All right, and 44 plus 273 Kelvin. So the lower temperature becomes the TL and higher temperature becomes the TH. It need not be given that the higher temperature is this and that. So that has to be understood. And then what is the coefficient of performance? So directly your COP, as this is a Carnot, is equal to desired effect by work done, that is equal to desired effect is this in a refrigeration cycle. So that will be minus 30 plus 273 by PH minus 44 minus of minus 30. Because temperature difference, I have removed the 273. So on calculation, it gives 3.2837. All right. Next, they have asked if the actual The refrigerator has a COP that is 70% of the Carnot work. So COP actual is equal to 0.7 into 3.2837. And then they're asking us to estimate the refrigeration effect per kilowatt of power consumption. So W is equal to 1 kilowatt. So what is the desired effect is what they are asking. So into 0.7 gives COP is equal to 2.299, and that is equal to your desired effect by work done. So desired effect is equal to 2.299 watts. Let's go to our third problem. A heat pump is to be used to heat a house in winter and then reverse to cool the house in summer. So the same equipment is being used as heat pump in winter and then as a refrigerator in summer. Then the interior temperature is to be maintained at 20 degrees centigrade. Heat transfer through the walls and roof is estimated to be 0.525 kilojoule per second. Okay. Per degree temperature difference between the inside and outside. Okay, this is nice. If the outside temperature is in winter is 5 degrees centigrade, what is the minimum power required to drive the pump? So let's do the A part first. So it is winter and it is a heat pump. So this is your desired effect. What is your lower temperature in winter? It is outside, which is equal to 5 degrees. So 5 plus 273. 278 Kelvin. Okay, and then your interior is your higher temperature. 20 plus 273 is 293 Kelvin. And then they are saying that heat transfer through the walls and roof is estimated. So there is a heat transfer which is equal to 0.525 kilojoule per delta C difference, right? So that is equal to 0.525 into the difference here is 20 minus 5, so 15 kilojoules inside and outside. What is the minimum power required? I think this is actually kilojoule per second, right? So it is actually kilowatt. Okay. What is the minimum power? So the word minimum is important because minimum power means maximum efficiency. This means Carnot efficiency. This is the keyword in this question. Efficiency is given by Carnot efficiency or COP as well. So COP is equal to desired effect by W. The desired effect in this case 293 by delta is 50. This is a COP. And then okay, so now the question is to maintain the temperature at 20 degrees centigrade. You have to remove this much of, you have to add this much of heat because this much of heat is being transferred. So that will be equivalent to your desired effect. So that is 0.525 into by WD. So here you get WD. Okay. Case 2. Case 2 is the summer case. All right. If the power input is same as in part A, what is the maximum outer temperature for which the inside can be maintained at 20 degrees centigrade? Okay, so we have to find out what is the power. 293 by 15 goes into denominator into 0.525 into 15, 0.403 kilowatt. 0.403 kilowatt. So now your work done is same is equal to 0.403 kilowatts, and they're saying that what is the maximum outer temperature. Again, the maximum outer temperature means it is a Carnot cycle. So outer temperature for which the inside can be maintained at 20 degrees centigrade. So heat rate is same here also, and it is equal to 0.525 in kilojoule per second into degree C difference. Here we do not, excuse me, what is the difference? So we write it as T minus 293, 0.525 into T minus 293. So this is the amount in kilowatts. So COP is equal to QL by W, that is equal to TL by TH minus TL, that is equal to 525 T minus 293 by 403. Is equal to 293 by T minus 2. So on solving this, you get T is equal to 308 Kelvin. All right. So this is an interesting thing. So you have to find T. You get T because there is a multiplication of T here. You get a quadratic equation in T. So on solving, you'll get two roots, and one of them is going to be a positive and real. So that is going to be your solution. Okay, in the fourth question, it is given that an inventor claims to have designed a heat engine which absorbs 1 kilojoule of energy as heat at 727 degrees centigrade and delivers 0.6 kilojoules of work when the ambient temperature is 27 degrees centigrade. Would you agree with this claim? So basically, a claim is either true or false. It is true if efficiency actual is less than efficiency Carnot, and it is false when opposite of this happens. Even when it is equal to efficiency of Carnot, it is not a correct claim. Okay. So now let's solve it. So here it is given that it is a heat engine first of all, and Qn is equal to 1 kilojoule, and pH is equal to 727 degrees. That is equal to 1000 Kelvin, and deliver 0.6 kilojoules of work. So work is equal to 0.6 kilojoules, and here TL is equal to 27 degrees centigrade. Efficiency actual is equal to W by Q is equal to 0.6. And efficiency Carnot is equal to 1 minus TL by is equal to 1 minus 300. So efficiency actual is actually less than efficiency Carnot. So it is possible. Okay. Now let's go to our next question. Question number 5. Two different fuels can be used in a heat engine operating between the fuel burning temperatures and a low temperature of 350 Kelvin. The fuel A burns at 250 Kelvin, delivering 52,000 kilojoule per kg and costs 1.75 per kg. Fuel B burns at 1700 Kelvin, delivering 40,000 kilojoule per kg and costs 1.5 per kg. Which fuel do you use and why? So basically there are two cases, the A case and the B case, and you have to see which one is more economical. Basically, that is what decides which one you are going to use. So let's do it. In the first case, burning, in both the cases, TL is equal to 350 Kelvin, right? And fuel A, here TH is equal to 2500 Kelvin, and here TH is equal to 1700 Kelvin. And then here, let's say this is calorific value of fuel is equal to 52,000 kilojoule per kg, and the cost is 1.75 per kg. All right. So fuel 2 calorific value is 40,000 kilojoule per kg, and costs 1.50 per kg. Which fuel do you use and why? All right. In the first case, in both cases, let's consider it as an Carnot cycle and find the efficiency, because without that we cannot proceed this question. And considering both to be Carnot, so because this is a comparative study, we can use this kind of analysis, because in comparison and we are using the same assumptions for both, so it is not a problem. So in the first case, efficiency is equal to 1 minus TL by PH, which is equal to 1 minus 350 by 2500. 350 by 2500 equal to 0.14, so it is 0.86. Efficiency is 0.86, and for this the efficiency is equal to 1 minus TL by PH. So always try to write the formula when solving. At least in practice, this during practicing your problems, please try to write the formula and then substitute the values, because that will help you to remember the formula much better, and also it will help you not to make any mistakes in substituting the values. Yes, writing the formula will take some extra few seconds, but I think it is always good to write the formula and investing those seconds to make sure that you do not make any kind of silly mistake. 350 by 1700. This is 0.79. All right. So now, let's do calculations per kg. Let's say we are using 1 kg of fuel of A and or 1 kg of fuel B. So in the first case, your Q in is equal to 52,000 kilojoule, and that will give you a work which is equal to efficiency into Q in, which is equal to some value. 0.86 into 52 44720 kilojoule. And in case 2, your Q in is equal to 40,000 kilojoule, and your work is equal to 0.79 into 40,000, which is equal to 31600. So this much amount of energy or work is produced. So now let's see what is the work produced per 1 rupee. So that will give us a comparative analysis. So here 44720 by 1.75, and here it is 31600 by 1. It is equal to 21066.6, and here it is 44705 25554. So for 1 rupee, we are getting more amount of work in A case. So fuel A is all right. Let's go to the next problem. Sixth problem. Two Carnot heat engines are operating in series such that the heat sink of the first of the engine serves as the heat source of the second engine. If the source temperature of the first engine is 1600 Kelvin and the sink temperature of the second engine is 300 Kelvin, and the thermal efficiencies of both the engines are the same, the temperature of the intermediate reservoir is. Actually, we have seen this as a formula, but let's try to solve it. So these are in series, and it is given both of them are Carnot. They are in series. These are the important keywords, and the source of the first is 1600 Kelvin and 300 Kelvin as the sink of the second, and this has an efficiency 1, efficiency 2, efficiency work done in 1 and work done. Given efficiency 1 is equal to efficiency 2, and we have to find what is this intermediate temperature. So efficiency 1 is equal to 1 minus T by 1600, right? For this heat engine, T is your lower limit, so 1 minus TL by TH is equal to this. In the second case, T is the higher temperature limit, so 1 minus 300 by T is your efficiency of the second heat. So when you're equating these two, you get T square is equal to 1600 into 300. T is equal to square root of 16 into 3 into 100. This is how we are going. But actually, you have to understand that T is equal to square root of T min into T max. This is what we are saying, right? We are seeing few extra formulas as well. So you can consider them as different problems as like this and solve them and try to generate those formulas, so that you will not have a problem even when you forget those formulas. Let's go to our next question, question number 7. An inventor claims that heat engine has the following specifications. So power developed is equal to 50 kilowatt, fuel burned per hour, fuel per hour is equal to 3 kg, and heating value or calorific value is equal to 75,000 kilojoule per kg, and then temperature limits TH is equal to 627 plus 273 for the 900 Kelvin, and then TL is equal to 27 plus 273 is equal to 300 Kelvin, and then we have cost of fuel is equal to 30 per kg, and value of power, and it is given the selling price is equal to 5 per kilowatt hour, and 1 kilowatt hour is equal to 3600 kilowatt. So this has to be remembered. All right. So first, let's see. If you look at the options, it is given the performance of the engine is possible or not possible, economical or uneconomical. So If it is not possible, it will be direct. You don't have to go into the second stage. But if it is possible, then you have to see if it is economical and uneconomical based on the selling price and the cost price. So let's see if it is possible or not possible. So possible or not possible, we have to find the actual efficiency and the Carnot efficiency. So we know that Carnot efficiency 1 minus TL by TH equal to 1 minus the TL is 300, TH is 900. So 1 minus 1 by 3 is equal to 2 by is 66.67%. And actual is equal to work done by Q, right? Yeah, 50 kilowatts is being generated. So 50 into, let's say for 1 hour, kilowatts is per second. So for 1 hour, there are 3600 seconds. So this much of kilojoules of work is done, and heat Q in is coming from your heating value 75,000 kilojoule per kg, and it is consuming 3 kgs of fuel per hour. So as we have considered this as for hour, it is also per hour we have to consider, and this will give us a value of 0.8. So actual is actually greater than your Carnot. So this is not possible. So we don't even have to go into the economical or uneconomical part. So if it is a possible cycle, then you go into the, how are you going to do? So you're going to first find what is the cost per kilowatt hour or cost per something. Maybe cost per kilowatt hour is the best case because selling price is also in kilowatt hour. So what is the cost per kilowatt hour? You find out and then find the selling price. You have the efficiencies, you have the cost of fuel that you can find. Next, let's go to the 8th problem. Okay, in an 8th problem, a window air conditioner consumes 1 kilowatt of electricity when running and has a coefficient of performance of 4, is placed in the middle of the room and is plugged in. The rate of cooling or heating the air conditioner will provide to the air in the room when running is. So this is a nice and tricky question. I request every one of you to pause the video for just a minute and just see what they are asking in the question. So this is a question that is based on your understanding of the wordings that are given in the question. So let me go into the solution. So they have given this as a room and they have the air conditioner in the center of the room. Actually, in our homes, we have air conditioner at the end. So it takes away heat from the inside and rejects it to outside. But in this case, it is taking heat from the room and rejecting to the room. So the net effect of the refrigerator is 0, except that it is using some kind of power which will actually increase the amount of heat that is being rejected, right? So for example, this is your refrigerator. It is taking some amount of Q from your room and it is again giving, and it is taking this much of Q. So Q plus W. So Q plus W amount of heat is given to the room. So basically you are adding heat which is equal to W, or the power that is being consumed by that refrigerator. So the answer is 1 kilojoule per second heating. Yeah, this is a very simple question, but it is a little tricky. Once you solve a number of problems, you will be very convenient with this. So they have given COP in the question which has no any relation with the calculation. So don't try to use every data that is given in the questions. Sometimes your data is dummy. So ninth question. In the figure E is a heat engine. In the figure, E is a heat engine with efficiency of 0.4 and R is a refrigerator. Given that Q2 plus Q4 is equal to 3Q1, the COP of the refrigerators. And if you look at the options, the COP is a constant term, so they have got a proper COP. So that means because none of the values are given here and only relations are given, you have to convert the COP into one quantity so that it cancels everywhere and then you can get a single value. For example, you'll understand when we are solving this question. So this is your Q1, Q2, Q3, Q4, E, R. Okay. So in the first question, it is given that efficiency is equal to 0.4, and we know that efficiency is equal to Q1 minus Q2 by Q1, right? 1 minus Q2 by Q1 is equal to 0.4. So Q2 by Q1 is equal to 0.6 and Q2 is equal to 0.6 Q1. So this is your first one. You have changed Q2 in terms of Q1. So similarly, you have to change Q3 and Q4 also. Because COP is equal to desired effort, as this is a refrigerator, it will be Q3 by work done, W. And your W is equal to Q1 minus Q2 because work is coming from the engine. So now you have to convert Q3 also in terms of Q1. So and then the Q1 gets cancelled in both numerator and denominator. For that purpose, they have given this relation. Q3 plus Q4 is equal to 3Q1. Okay. Q3 plus Q4 is equal to 3Q1. And we know that W plus Q3 is equal to Q4, right? By first law. If you are applying W plus Q3 is equal to Q4 and W is equal to Q1 minus Q2 plus Q3 is equal to Q4. If Q4, if you substitute here, Q3 plus Q4 is nothing but Q1 minus Q2 plus Q3 is equal to 3Q1. So 2Q3 is equal to Q1 minus Q2. Q1 minus Q2 is equal to 0.4 Q1, right? Okay. Sorry. Oh, okay. 2Q3 plus Q1 minus Q2 is equal to 0.4 Q1 is equal to 3Q1. So 2Q3 is equal to 3 minus 0.4 is 2.6 Q1. Q3 is equal to 1.3. So now you have all the values of COP in terms of Q1. And now as you substitute, you'll get the answer. I think the answer is 5. COP is equal to. Let's go to the next question, 10th question. A heat engine operating between two reservoirs of 1000 Kelvin and 300 Kelvin is used to drive a heat pump, which extracts heat from the reservoir at 300 Kelvin at a rate twice that at which the engine rejects heat to it. If the efficiency of the engine is 40% of the maximum possible and the COP of the heat pump is 50% of the maximum possible, what is the temperature of the reservoir to which the heat pump rejects heat? What is the rate of heat rejected from the heat pump if the rate of heat supply to the engine is 50 kilowatt? Okay. So basically there is a heat engine which is giving work to a heat pump. This is your heat pump. This is your heat engine. Okay. Another heat engine is operating between 1000 300. Extracts heat from 300. And if this is Q1, Q2, Q3, Q4, it is given that Q3 is equal to 2Q1. Okay. If the efficiency of the engine is 40% of maximum possible, so efficiency Carnot for the heat engine is equal to 1 minus 300 by 1000, that is equal to 0.7. So efficiency of heat engine actual is equal to 0.4 into 0.7 is equal to 0.28. All right. Now let's come to the next part. COP of the heat pump is 50% of the maximum possible. COP of the heat pump is equal to what? Actual COP is desired effect. This is the heat pump desired effect is Q4 by W is equal to 0.5 into your Carnot COP, maximum possible COP. Let's say this is T. Desired is T by T minus 3. All right. Now we have to find what is Q4. What is the temperature of reservoir to which the heat pump rejects heat? So now again we are going to use the same funda as we used in the previous problem, that we are going to convert both Q4 and W in terms of one quantity so that it gets cancelled out, and then we can find temperature directly. So we have already that Q1 by W, sorry, W by Q1 is equal to 0.7. So W is equal to 0.7, right? And now Q4 is equal to W plus Q3, and Q3 is equal to 2Q2, right? 2Q2, yeah, 2Q2, and Q1 by Q2 is equal to 1 minus efficiency equal 0.3. Q2 by Q1. Okay. So Q2 is equal to 0.3 Q1. So Q3 is equal to 0.6 Q1. So Q4 is equal to W equal to 0.7 plus 0.6 Q1, 1.3 Q1. So now you have got Q4 is equal to 1.3 Q1. So 1.3 by W is equal to 0.6. Q1 by Q1 gets cancelled. So now you can directly find temperature. So once you get temperature, you get COP Carnot, and that gives COP actual is equal to 0.5 into that, and then you can find the heat supply to the engine, etc. Next, let's go to our next question. 11th question. In 11th question, it is given a cyclic device operates between 3 thermal reservoirs as shown in the figure, and heat transfer to from the cycle device. It is assumed that the heat transfer between each thermal reservoir and the cyclic device takes place across invisible temperature difference. Interactions between the cyclic device and the respective thermal reservoirs are shown in all forms of the heat transfer. So cycle device can be reversible heat pump or a refrigerator, heat engine, or etc. Okay, so first we have to find if it is reversible or irreversible, and then we have to find if it is a heat engine or a refrigerator or heat pump. So for reversible or irreversible, we have the Clausius, because these are all cyclic devices. Clausius is dq by t is equal to 0, reversible less than 0, irreversible, right? So let's calculate Clausius. You have to take sign conventions into account. So in the first case, 100 is coming into the system, so it is positive by 1000, and then for the 500 is also coming into the system, so plus 50 by 500, but next it is leaving minus 60 by 300. So this is 0.1, this is also 0.1 minus 0.4, so this is equal to 0. So it is a reversible process. Now what, heat engine or heat pump or refrigerator, what is it? So let's see what is Q in, what is the amount of Q in. So it is taking in 100 plus 50, so 150 kilojoules total heat is inputted into the system, and how much is rejected? Rejected is 60. So basically work is done, because work is equal to Qn minus Qr, and this is positive here, which is equal to 150 minus 60. So 90 kilojoules of work is being done. So this means that it is a heat engine, because refrigerator and heat pump, we have work is done on the system, and it is not work done by the system. So it is a reversible heat engine. So next lecture, let's go into the entropy concept. Thank you.